Frame relay has become the most widely used WAN technology in the world. Therefore, network engineers need to be prepared to deploy and troubleshoot this protocol. This video explains the basic concepts of this high-performance WAN protocol. Large enterprises, governments, ISPs, and small businesses use Frame relay primarily because of its price and flexibility. As organizations grow and depend more and more on reliable data transport, traditional leased line solutions become prohibitively expensive. Frame relay reduces network costs because equipment requirements are low, it is not complex, and it is easy to implement. Moreover, Frame relay provides greater bandwidth, reliability, and resiliency than private or leased lines. With increasing globalization and the growth of one-to-many branch office topologies, Frame relay offers simpler network architecture and lower cost of ownership. As a data link protocol, Frame relay provides access to a network, delimits and delivers frames in proper order, and recognizes transmission errors through a standard cyclic redundancy check. Frame relay can also provide multiple logical connections over a single physical circuit and allows the network to route data over those connections to its intended destinations. When carriers use Frame relay to interconnect LANs, a router on each LAN is the DTE. A serial connection, such as a T1-E1 leased line, connects the router to the Frame relay switch of the carrier at the carrier's nearest point of presence, or POP. The Frame relay switch is a DCE device. Network switches move frames from one DTE across the network and deliver frames to other DTEs by way of the DCEs. The connection through a Frame relay network between two DTEs is called a virtual circuit, or VC. The circuits are virtual because there is no direct electrical connection from end to end. Instead, the connection is logical. With virtual circuits, Frame relay shares the bandwidth among multiple users, and any site can communicate with any other site without using multiple dedicated physical lines. In this video, there is a VC between the sending and receiving nodes. The VC follows the path A, B, C, and D. Frame relay creates a VC by storing input port to output port mapping in the memory of each switch, and thus links one switch to another until a continuous path from one end of the circuit to the other is identified. A VC can pass through any number of intermediate switches located within the Frame relay network. The question you may ask at this point is, how are the various nodes and switches identified? VCs provide a bidirectional communication path from one device to another. They are identified by data link connection identifiers, or DLCIs. DLCI values typically are assigned by the Frame relay service provider, for example the telephone company, and have local significance, which means that the values themselves are not unique in the Frame relay WAN. A DLCI identifies a VC to the equipment at an endpoint and has no significance beyond that single link. Two devices connected by a VC may use a different DLCI value to refer to the same connection. Locally significant DLCIs have become the primary method of addressing because the same address can be used in several different locations while still referring to different connections. Local addressing prevents a customer from running out of DLCIs as the network grows. This is the same network presented in the previous figure, but this time as the frame moves across the network, Frame relay labels each VC with a DLCI. The DLCI is stored in the address field of every frame transmitted to tell the network how the frame should be routed. In this example, the frame uses DLCI 102. It leaves the router using port 0 and VC 102. At switch A, the frame exits port 1 using VC 432. This process of VC port mapping continues through the WAN until the frame reaches its destination at DLCI 201. Since Frame relay is a Layer 2 protocol, it needs a mechanism for mapping to a Layer 3 address. Frame relay has two methods, dynamic mapping, which relies on inverse ARP, and static mapping. The Inverse Address Resolution Protocol, or inverse ARP, obtains Layer 3 addresses of other stations from Layer 2 DLCI. Whereas ARP resolves Layer 3 addresses to Layer 2 addresses, inverse ARP does the opposite. The router builds and maintains this mapping table, which contains all resolved inverse ARP requests, including both dynamic and static mapping entries. On Cisco routers, inverse ARP is enabled by default for all protocols enabled on the physical interface. The network administrator can choose to override dynamic inverse ARP mapping by supplying a manual static mapping for the next hop protocol address to a local DLCI. An example of using static address mapping is a situation in which the router at the other side of the frame relay network does not support dynamic inverse ARP. In this example, static address mapping is performed on interface serial 000, and the frame relay encapsulation used on DLCI 102 is Cisco. As seen in the configuration steps, static mapping of the address using the frame relay map command allows users to select the type of frame relay encapsulation used on a per VC basis. Static mapping configuration should be studied and practiced in more detail after viewing this video. Another concept network engineers need to understand is Local Management Interface, or LMI. The LMI is a keep-alive mechanism that provides status information about frame relay connections between the router, or DTE, and the frame relay switch, or DCE. Notice the amount of information available via the LMI. This video supplied an overview of the basic frame relay concepts. As with most networking protocols, there are many more concepts and details to learn and configurations to practice. Since frame relay is the most used WAN technology in the world, network engineers must have a solid grasp of this protocol.